How are Gibbs free energy and the equilibrium constant K related? Imagine a reaction as a balance beam, constantly shifting. Sometimes it favors products, sometimes reactants, and other times it stays steady. How do we predict which way it will tip? That's where Gibbs free energy and the equilibrium constant come into play. They are like two sides of the same coin, helping us understand whether a reaction will happen on its own and how far it will go. Gibbs free energy, often written as G, measures the maximum useful work you can get from a reaction at constant temperature and pressure. If the change in Gibbs free energy, called delta G, is negative, the reaction can happen spontaneously. If delta G is 0, the system is at a point called equilibrium, where nothing changes. When delta G is positive, the reaction needs energy input to proceed and is non-spontaneous. Now the equilibrium constant, which we call K, tells us the ratio of products to reactants when the reaction reaches balance. If K is greater than 1, it means there are more products than reactants at equilibrium. If K is less than 1, reactants dominate. When K equals 1, both sides are balanced. The magic happens with a special equation that links these two ideas. Delta G standard equals negative R times T times the natural logarithm of K here. R is the universal gas constant, about 8.31 for joules per mole per Kelvin, and T is the temperature in kelvins. The natural logarithm, written as lane, helps us see how changes in K affect delta G. If delta G standard is negative, then lane K is positive, which means K is greater than 1. The reaction favors products and is spontaneous. If delta G standard is positive, lane K is negative, so K is less than 1, favoring reactants. When delta G standard is 0, lane K is 0, so K equals 1, indicating the reaction is at equilibrium. At equilibrium, the actual Gibbs free energy change, delta G, is 0. That means the system has no tendency to change further. If the reaction quotient Q, which is the ratio of current concentrations, is less than K, delta G is negative, and the reaction will move forward to produce more products. If Q is greater than K, delta G is positive, and the reaction shifts back toward reactants. This relationship helps chemists predict how reactions behave. By knowing the standard Gibbs free energy change, they can find out the equilibrium constant and vice versa. It's a powerful tool for understanding how energy and concentration work together to determine whether a reaction will happen spontaneously and how, for it will go before settling into balance. Whether in the lab or in nature, this link makes the principles of thermodynamics easier to see in action.